All right, so let's talk about motion in a straight line, and let's just remember some of our function names. So let's recall that v of t denotes the velocity of an object moving in a straight line. And for the purposes here, we know velocity is equal to the derivative of our position function. So our position function is s of t, and the derivative of that is the velocity. So we're going to be looking at, for the most part, the rest of this lesson is going to involve looking at displacement for an object moving in a straight line and the total distance traveled by an object moving in a straight line. So these are two slightly different quantities that we're going to be looking at, but also very similar to something we've done before. All right, so to help with this, we have a little example here. So we have an object, some object moving in a straight line, and we've graphed the velocity function. So it's a nice kind of linear velocity function here, just to make it easy for our little discussion. So this is the graph of our velocity function. Let's actually have a little diagram going for our object that's moving around. So let's draw we'll use a vertical line here. And so our object is sitting somewhere on this line, and what's going to happen is it's going to be moving around. So let's suppose this is where our object starts. So this is our starting position. All right, and according to the graph, we're starting at 0. Something interesting happens at time c, and then we're ending at time d. So our starting position, we're starting this at t equals 0. All right, so let's think about how this object's going to move around based on this graph of its velocity. So in this section right here, from 0 to c, during this time interval, the velocity is positive. We can see that the velocity of the object, the graph of the velocity, is above the horizontal axis, so that means it's a positive velocity. So that means our object is moving in the positive direction. So let's suppose, based on this object in this straight line here, that up is the positive direction and down is the negative direction. Think the y-axis. So normally we use up as positive and down as negative. So we'll use that here. All right, so in this interval from 0 to c, our velocity is positive. So what's happening is during that time interval, we have some starting position, and we're moving up. And then we get to this moment in time at t equals c, where we're moving up and we start slowing down. So let's look at the graph here. Our velocity is still positive, but it's less and less and less. So it means our object is slowing down. It's still moving up, but it's slowing down. And then at time c here, what happens? Well, our velocity becomes 0. So at this moment in time, at t equals c, our object is moving up and up and up, but it's slowing down, and then at t equals c, it stops. So it kind of reaches a high point. And then what happens? Well, if we look on our graph, the velocity becomes negative. So we have a negative velocity. So what that means is the object starts moving again, but now it's moving in the negative direction. So it starts moving down. So what happens is at time 0, we're moving up, and we keep moving up. We're slowing down, but we're still moving up. And then at time c, we stop. And then after that, we're moving in the negative direction, so we're moving down. And then we get to some point, maybe here. Doesn't necessarily have to be the halfway. Maybe, let's see here. Maybe right here. This is our t equals d. So these are just like little snapshots in time of where our object is. So at t equals 0, we're here, and then it's moving up. We get to this high point, and then we fall down, and then we're right here. And this is our ending position. All right, so this is just interpreting the graph here. All right, so the two quantities we're going to be interested in for an object that's moving around is displacement and the total distance traveled. So let's think about displacement based on these different positions here. And what displacement does is it measures only the distance and the direction between our starting position and the ending position of our object. So looking at this little diagram here, the displacement is right here. This distance here, the difference between these two locations is our displacement. It's our ending position minus our starting position. So in this case, the displacement is in the positive direction, and we've moved up a little bit. So displacement would be positive in this case. All right, so how do we actually calculate displacement? So the displacement over some time interval from a to b is just the definite integral from a to b of our velocity function. That's what we saw with the net change theorem. So how do we interpret this, or how could we interpret this based on these regions under the curve? So really what we're doing with displacement is we're measuring the distance that we travel in the positive direction, and we're subtracting off the distance that we travel in the negative direction. And so if our distance in the positive direction, if the distance we travel in the positive direction is bigger than the difference that we travel in the negative direction, well then the net effect here, the net change, is we're going to have a positive displacement. If we travel the same distance in the positive direction and we travel the same distance in the negative direction, well then they're going to balance out and the displacement's going to be 0. So we're going to have a starting position, we move around, and then we end up back exactly where we started. So in that case, the displacement would be 0. And if we travel further in the negative direction, well then that means we're going to be moving further down. So the displacement is going to be somewhere in this, it's going to be negative. Our ending position will be kind of below our starting position. So that's how we can think of displacement. It's the distance we travel in the positive direction minus the distance that we travel in the negative direction. Now, we can think of this in terms of area under the curve. So if we look at our velocity function here, if we were to calculate the area for this shaded region, well, that's just the area above the horizontal axis. And what that really describes is this area here really describes the distance that we're traveling in the positive direction. And if we were to calculate the area for this region that lies below the horizontal axis, what this area represents is it represents the distance that we travel in the negative direction. So the area below the horizontal axis is the distance we're traveling in the negative direction. So we've seen this quantity before, area above minus the area below. We called that the net area. So now we're kind of expanding that to the context of displacement. So if we integrate this velocity function from a to b, we're really calculating the distance that we travel in the positive direction, which really can be thought of as just area under the curve that's above, minus the distance that we're traveling in the negative direction. And we can think of that distance that we're traveling in the negative direction as just being this area for the region that's below the horizontal. Now the total distance that we travel, what does this represent? Well, this measures it measures the total distance that we traveled during that entire time interval. So it kind of captures everything. Even when we kind of retrace our footsteps, it includes all of that. So we have this object. Let's go back to our little motion video here. We have this object. It's starting. It goes up and up and up. It slows down, hits time C here where it stops, and then it starts retracing its steps, and then we have our ending position. So what the total distance does is it records it just records the distance and gets rid of any direction considerations. So the total distance for this object would capture how much distance we traveled up, and it would also capture how much distance we traveled down, and just add those two together. So it kind of strips away any consideration for direction. We're just trying to figure out how much did we travel here. So we went up this much, and then we went down this much, and we just add those two distances together. So if you were to think kind of running back and forth, if you were running on a track, maybe on a bike path or something, and you did some laps back and forth, you're going to be more interested, for yourself in how much did you actually run going back and forth. Most likely your displacement, if you start and finish at the same place, your displacement is 0, but you're interested in how much distance you actually covered going back and forth. So that's what we're capturing here with this total distance, is how much did I move regardless of direction. And so this is going to be the integral of the absolute value of our velocity function. And thinking of this in terms of area under the curve, or these regions under the curve here, the way to calculate this definite integral is we're going to do the distance that we travel in the positive direction, and instead of subtracting off the distance that we travel in the negative direction, what we're going to do is we're just going to add in the distance that we travel in the negative direction. So we don't care about the direction here. We just want to know how much did I travel going up, how much did I travel going down, and I just add those two results together. So it's the distance up plus the distance down, and we're just adding those together. So if we think of it in terms of region under the graph, it would be the area of this region plus the area for this region. So it would be the area above plus the area below. So this is the same thing we were talking about with area calculations. We had net area and total area. Displacement is kind of equivalent or similar to the net area, and total distance is similar to the total area under the curve. All right, so we're going to see how to calculate these in a few examples. So we'll see you there.